admin before, so like up to grade. What did you have for a fourth? Mythbusting. I hated research methods.
Oh, I want to do research, so like.
Oh, that's right up your alley, but I didn't really enjoy it, so I don't want to do anything with research after graduation, so.
Sorry. I need this. Yes. It's got an ad.
Plus, I'm like hoping I can get a new Dr. Harder because I'm like one of those like.
Like the tutors or
Yeah.
being in the office all the time?
Both.
Oh, that's cool. Yeah. As long as you, I don't even know how to tell you to get on his good side because there really is no way. I think he just makes like his own influence whether or not he likes it.
I mean, I think I'm already on the good side, but.
As long as you like, for research methods at least, like, I think you like me, so as long as you email him a lot, ask him questions in class, like, go to his office hours, you'll be fine, and he'll like you, but if you don't put in the effort, that's when he kind of starts to. Did he say anything if you guys would do the, like, presentations? I didn't know if they were gonna allow it because of COVID or not. Got any fun plans for the weekend, Paul or Sean?
Huh?
Got any fun plans for the weekend?
No. I'm a boring person. I am boring. Work. Yes. Allison, can you hear me? You're muted.
Yeah, I can hear you.
Pete, what do you see?
I can't
What do
see you though.
That's good. Do you see words?
Yes, I can see the PowerPoint.
Beautiful. That's what we're gonna do. Because otherwise you get that like 45-degree angle of the screen, right? And you don't see really anything.
Yeah, it's a lot better this way.
Good, good. What you're saying is you don't want to see us. That's fine.
No, I'm not quite.
I'm totally joking. Don't worry. Okay. Before we start writing, let's pray. Father, Son, Holy Spirit. God, grant me the serenity to accept the things I cannot change, courage to change the things I can, and the wisdom to know the difference. Father, Son, Holy Spirit. Amen. So we did all of these yesterday, or Tuesday. Talked about these, right? So if you haven't filled those in, you will have some time to fill those in a little bit. I want to move on. So this is just the overview. So neuropsychopharmacology, study of chemical substances that act on the nervous system in a way that alters our behavior. We're going to talk about all three of these components. We will talk about the neuro, but before we do that, let's talk about, just real briefly, about how drugs work. So when we're talking about the drugs themselves, there's 4 different categories of, I guess, stuff, very technical term, that we want to be able to pay attention to and distinguish. The first is what's called the drug action. So the drug action, this is the specific molecular changes. So the drug action relates to the specific molecular changes produced by a drug. Produced by a drug when it binds to its active site. Its active site or site of action. Okay, so that's drug action. We're going to distinguish the drug action from its effects. The drug effects. These are 2 different things. One is going to lead to the other, right? So the one leads to the other. So drug effects. We can define, this is your book, defines this as the changes in, yeah, I'm really good at making the chalk squeak. Physiological, so it's changes in the physiological and or psychological functions. So the drug effects are the changes in the physiological and or psychological functions that are the consequences of the drug action, right? So these are the consequences of drug action. A leads to B. So, let's go back. Find these. Okay, with the big arrow here, right? So, let's take a look at let's go back to our paper. Let's go back to our paper from Tuesday. And I told you what the drug action was. So we're talking about morphine. So what's the drug action of morphine? Do you guys remember? Oh, Allison.
So wouldn't the drug action be the molecular change that would have happened when the morphine binded to the nociceptor?
Yes. So, and we get a specific name, which is mu. So the drug action of morphine is to activate mu opioid receptor. So the drug action of morphine is to bind to and activate mu opioid receptors. Can you see the board from over there? Okay. That's the drug action. What were some of the drug effects? So I want to clarify, Allison, it's not binding to, why am I staring at the screen? You can't see. I was trying to look at you, your pictures on the, anyways, whatever. So, it doesn't bind to the nociceptors. You're still, those receptors are still working. They're still sending pain signals up to the central nervous system. But when you activate the mu opioid receptors, you sort of stop, you ultimately stop that network, right? You block that at some point. Okay, drug effects. So what are the drug effects? We talked about some of the drug effects. I'm going to go to Allison. Allison, what are one of the drug effects of morphine?
We said that it appeared as though they were sleeping.
Okay, so one could be sleeping if you have too much. This is actually good because this will give us, does Santa Claus still see you when you have too much morphine? It sees you when you're sleeping. Anyways, all right. Yo, that's called associative cortex action. Okay, that's one. What's some more?
So it just like blocks like the same signal that's releasing.
Good. So reducing, we could say analgesia is a better. Good. Analgesia. That's a drug effect. Anyone else? That
Messes up your stomach.
constipation. Ultimately, okay? And nausea, actually. Yeah, it can cause nausea, right? So let's say nausea. Okay, good. So these are all drug effects, the result of the action of morphine activating mu opioid receptors. Awesome. Now, I think we can say, but not all effects are the same, are they? So there are effects that we desire, and there are effects that we do not desire. So therapy. So therapeutic effects just very basically, simply defined as the desired drug effects. What we're looking for. If you're in pain, you just had an invasive surgery, you're in pain, the doctor gives you a prescription for some opioids. Yeah, day one, I'm popping that bad boy. Pain goes away. Therapeutic effect. So analgesia here, I think we can identify very easily, or we should be able to identify as a therapeutic effect, right? Side effects. These are effects other than the desired drug effects. These are effects that are other than the desired effects. Now, sometimes if you are recovering, sleep is a good thing, right? Oh man, I haven't slept. So come in, 8 o'clock at night, you have pain, severe pain, you can't sleep, you can't sit comfortably in your bed or your recliner chair. I'm in pain and I want to sleep. Nice. Boom. I'll take my opioid. If it's during the day, sleeping might be a side effect, but nausea would certainly be a side effect. And anything that would not be a desired effect, we would consider that to be a side effect. Any other side effects that we talked about of morphine?
I don't
Yeah,
know
John.
if we talked about this one, maybe dizziness.
Yeah, sure. Absolutely. But so let's say sleeping, what's one of the things one of the warnings they always put on the pill vial, which is don't
Drink. One.
Okay, you definitely don't want to drink.
Don't try.
Don't operate heavy machinery.
Yeah.
I'm gonna go out and run that drag line today. I'll be right back. No. Right. So don't drink. Is that what you're gonna say? Right. So in that case, sleepiness would be a side effect. Okay, I think you got the idea. Cool. So, basic. These are some basic things. We're going to be looking a lot. This is going to be the big one right here. We're really going to focus a lot on drug action, especially when we're going to dive into the synapse in a way that maybe you did in neuroscience, but we definitely don't do in physiology. There's a lot of funky stuff that happens in the synapse. And we're going to look at each of those things that can happen. And drugs can impact any of the variables of the synapse. Okay? And this can lead to actually contributing to the effects that we ultimately see. Some of those are beneficial, they're therapeutic. Some of those are not. All right, let's move on. So, that's drugs, drug effects, and we are mainly talking about how drugs are going to affect the nervous system. So the nervous system, it's one of the two major systems that regulates things in our bodies. The other one is the endocrine system. And the nervous system and the endocrine system, they're intimately connected. Right? But so there's three major functions of the nervous system. I'm just going to go over these real quickly. Is it receives sensory information? So the nervous system, it receives or detects sensory information. Number two, it's going to process or integrate this sensory information. Integrate, process, synthesize, whatever. And pull that information, like we sort of talked about on Tuesday. It's going to form a picture. Boom! What's happening? This is what's happening. Is a response required? Does something need to be corrected? Yes. No. Okay. And number 3, I use the word orchestrate. I guess that's more conducting, but all right, it's going to orchestrate, or we can say maybe initiate a neurological response. To these stimuli, if one is needed. Right, so that's the main function, 3 main functions of the nervous system. All right, and we've seen how this nervous system is organized. We've seen these maps before. How many have seen one of these maps before? All right. So we know we've got 2 major divisions of the nervous system. We've got the central and the peripheral. Central nervous system, it's doing all the processing, all the integrating, all the decision making happens. And the central nervous system is comprised of the brain and the spinal cord. This is all central nervous system. And then the peripheral nervous system. 2 major divisions, afferent and efferent. The afferent division is responsible for, afferent means arriving to the central nervous system, and its job is basically to communicate all of this sensory information, all of it, to the central nervous system. Afferent division. All those neurons, they're all coming into the central nervous system. We've got sensory neurons, we said over 1 billion in our skin. Most of those are just for pain. But we've got sensory neurons all over the place. In our blood vessels. Our skeletal muscles, smooth muscle. Most of the organs in our body, right, they have some sort of, it's going to be some kind of sensory receptor. Right, so when you see this map and you see sensory stimuli, that's the 5 senses. And then visceral stimuli, this would be information from your body. Information from your body. So that's afferent. So the morphine, we talked about the pain. Pain, we got nociceptors detecting that noxious stimulus. That information is all then being communicated to the brain and the spinal cord by means of these afferent division. All right. Now the other branch is the efferent division. So, receiving sensory information, processing it in the central nervous system. Now there's a response that's needed. All of that information is communicated to the body by means of the efferent division. And we typically just break these up into 2 big categories. We'll start with the one on the left here, which is called the somatic nervous system. When you hear the word soma, By the way, anyone ever read the book Brave New World? What's the drug that makes people happy? Called Soma. Yo, how you doing? But actually, Soma means fun. So these are motor neurons. This is typically what we call our voluntary nervous system, right? So if you're going to move your skeletal muscles, we call that voluntary, but there's a lot of the contracting and relaxing of our skeletal muscles is actually involuntary. Did you know that? Good. Did you know that, Allison? I see your forehead. Never mind. Okay. Second part, major branch, autonomic. Right, we call it the involuntary. We used to call it the involuntary nervous system. I'm going to talk a little bit. We may get into the guts at some point, probably not. So the enteric nervous system, I'm just going to briefly mention it. There are more neurons in the enteric nervous system than in your spinal cord. It's called the second brain. And you probably are aware of this, but they have over the last decade or a couple of decades, they've begun to identify what's called the gut-brain axis. There's a lot of communication between the gut and the brain that we didn't know before. Kind of cool, but we may not talk very much about that. But then the classic, the two divisions of the autonomic nervous system that most people talk about are the sympathetic and the parasympathetic divisions, right? And so here, this figure from your book, we're showing the sympathetic division on the left, parasympathetic on the right, and in general, it's not always the case, but in general, what we can see is that these neuronal pathways from the sympathetic division and parasympathetic oftentimes have inputs to the same organs, the same systems. All right? Not always, but oftentimes they do. And typically when the sympathetic division of the autonomic nervous system is activated, which means the activity of the neurons of the sympathetic division is increased. What kind of a general response do we call that? We call that the blank or blank response. Fight or flight response, right? So if we increase the activity of the sympathetic division, we got to go over these real quickly. Review fight or flight. If I increase the activity of the neurons of the parasympathetic division of the autonomic nervous system, what's the phrase we used? Do you remember? I'll give you the first word, Devin. Rest and rest and digest. It's good. I'm gonna cry tonight.
Right, well, I know what's going on there, but like, I don't know, fight or flight's obvious, rest and digest, yeah, that makes sense.
That's all right. Okay. And in general, if If I increase the activity of the sympathetic division of the autonomic nervous system, what happens to my heart rate? Think fight or flight. Increase, right? Heart rate is, instead of heart rate, heart rate will increase. And if sympathetic division, the activity of the sympathetic division decreases, what happens to the heart rate? Decrease. What about if the activity of the parasympathetic division increases? What happens to the heart rate? It's going to go down. And the activity of the parasympathetic division decreases, what's going to happen to heart rate, Julie? Right. So the other thing that we're going to see is that for most functions, if it's controlled by both sympathetic and parasympathetic divisions, they're going to work in opposition to each other. So this response right here wherein the sympathetic division is increased in the, oops. Yeah, that was wrong. Okay. That's, it will increase, and then we would see the parasympathetic activity, the parasympathetic going down at the same time. It's like driving. Get your gas, vroom, vroom. You got your brake, urge, urge. So if you're going to speed up, if you're going to accelerate, you don't just hit the gas, right? You're a stoplight. It turns green. You go, I'm going to go fast now. You got to let off the brake, right? Okay. So this is a classic example of a fight or flight response. When it comes to the GI tract, your stomach, your intestines, you are going to see the opposite effect. If you increase the activity of the sympathetic division, you will see reduced activity of the GI tract. So you go out for a run, your guts should be like, chill. As you reduce the activity of the sympathetic division, you should then expect to see an increase in the activity of the GI tract. Right? And we'll flip this around. If I increase the activity of the parasympathetic division, GI tract activity should increase because this is a rest and digest response. And if the activity of the parasympathetic goes down, right, that's associated with increased heart rate, you're going to reduce the activity of the GI tract. Okay. I'm just giving that to you to give you a little overview of these systems. This will be important because we might see some drugs eventually that not only will impact the brain, but because the brain is changes in brain activity can result in all kinds of changes in respiration, heart rate, gut activity, right? Then it may also impact one or other of these branches. So we'll stop there for a moment. Questions about that? In general. You good? Okay. Allison, you good?
Mm-hmm. Yep.
Okay. So let's talk about this brain, shall we? This is cool. All right. So before we do this, I just want to, let's go over. Okay, I kept this out of your way. Thank you very much. I don't even know what that means. All right. Go away. All right. So we're just going to take a look at some of the new technology that we're being able to develop about the wiring of the brain.
It's muted right now. I don't know if that matters.
Oh, that's right, because we had that advertisement. Thank you.
Oh, and then I'm not able to see it either.
You're not?
Is it a video?
Yeah.
Yeah, I can't see it.
Okay. Can you see that?
I'm only able to see your central nervous system PowerPoint.
Okay. Well, I guess we won't do that then. I can move. That's all right. That just like was only like my favorite part of the whole class. But that's all right. I'm joking, Allison. Okay. So let's talk about this brain, all right? So we're going to start at the lowest. We're going to start in the brainstem, and we're going to work our way up through the forebrain. The brainstem, actually, is comprised of, you notice we've got, we're gonna include the mesencephalon and the hindbrain in the brainstem. Okay, so all three, the purple, the green, and this salmon color, we're all gonna consider that to be the brainstem. And we're gonna come back to this picture multiple times, that way we can see where we are, all right? So let's talk about the brainstem. It's the most primitive, considered, I guess, the most primitive region of the brain, and continuous with the spinal cord, right? All right. So it contains, as I said, the midbrain, the mesencephalon, the pons, the medulla, and the cerebellum. So the brainstem contains all of those regions.
Can you say that again, please?
I certainly will. Contains the midbrain, which is also called the mesencephalon. Pons, the medulla, and the cerebellum. Now, I'm going to define something for you here. In the brain, in the central nervous system, there's collections of neuronal cell bodies. So neuronal cell body, that's what contains the nucleus in a neuron, the cell body, the soma. when you, in the brain, in the central nervous system, when you have a region where you have a collection of these neuronal cell bodies, those regions are called a nuclei. It's called a nuclei or a nucleus. So a brain nucleus is not a single cell. It's a collection of neuronal cell bodies. I just wanted to define that for you, so that way when I'm talking about the nucleus accumbens, which we'll talk about, you'll say, oh, is that like one, what, is that a neuron? No, it's a collection of neuronal cell bodies, okay? Now, they control primary life-sustaining functions like respiration, circulation, and digestion. Look, and we're going to talk a little bit about the cranial nerves, not too much, but there are pairs, our nerves, oftentimes in our bodies, are in pairs. Why pairs? One goes to the right side, one goes to the left side. Pairs of cranial nerves originate in the brainstem, and the brainstem also contains, we're going to see, they contain nuclei, collections of neuronal cell bodies, that send neuronal axons to higher brain regions, cerebral brain regions. Okay. All right, so let's break this down. Okay. Start with the myencephalon. The myencephalon is the medulla. Right? Medulla. Where are we here? Right here. Medulla. Salmon area. Okay. I said it has got these bundles of neuronal cell bodies called nuclei that control survival functions. Like heart rate, respiratory rate, digestion, and vomiting.
I have a question.
Yep.
Is that why whenever like a child or an adult would be diagnosed with a brain tumor, one of the first symptoms is vomiting?
So the brain tumor is going to be, what, if it begins to put pressure, Allison, and apply pressure in the brain, it then can ultimately begin activating some neuronal pathways that can activate that area. Yeah.
Okay.
Yeah. You guys did all kinds of things with the vomit reflex, didn't you? Really? Area post-treatment, did you guys talk about that?
What was it again?
Area post-treatment, the area post-treatment, no? Okay. Being dizzy, why that makes you more likely to puke than other times?
I had a like question on that a little briefly, but nobody goes about it.
So, good question. When you die of a drug overdose, not when you do, when someone dies of a drug overdose, okay? It's because of loss of function of the medulla.
So it's commonly called the medulla, but the proper name is myencephalon.
You got it.
Okay.
Yes, so the myencephalon is also known as the medulla. That's a good, but yes. So there's some sort of a, if you depress or shut down the brain, the medulla, the myencephalon, then it can no longer respond to drops in heart rate, drops in blood pressure, changes in carbon dioxide in the blood. It can't respond properly, and that's what happens. Cool. All right, other questions about that? All right, so let's move onward and upward. We're going to move into the green area, The metencephalon, still part of the hindbrain. Oh, wait a minute. No. Okay. Let's keep talking about the metencephalon. Okay. So the next section is the metencephalon. Pons and cerebellum. Pons and cerebellum. So now we're in the green area. Pons. Has the structure called the reticular formation. The reticular formation, and these are, the reticular formation contains nuclei, that's why I wanted to use that word, introduce that term for us today. Our nuclei control functions such as arousal, attention, sleep, and muscle tone. All right, so arousal. Oh, I'm awake. You ever been sleeping? You've never been sleeping. You ever been sleeping? You've been driving, and you're out there. You're on the interstate. It's not Pennsylvania. It's a smooth road, and you get that to tick, to tick, to tick, to tick. You're kind of by yourself. To tick, to tick, to tick, to tick, to tick. I gotta turn the radio on. And all of a sudden the car just kind of starts going to tick, to tick, to tick. You hear that, brrr. Okay, now I'm up. That's arousal. Attention, arousal and attention kind of seem the same, but attention is actually, I'm looking here. I'm looking here. I'm looking there. So if something gets your attention, yo! That's arousal, and then you look and you see who just yelled at you. That's attention, okay? Anyways, that's regulated in the pons, and so is sleep. Now the pons contains two important areas that we need to pay attention to. We're definitely going to be talking about these two areas. Here's where we start to get geeked out. Okay. It's going to contain two areas. Number one. Now the spelling of this is really weird, so the locus ceruleus. The locus ceruleus. Blue. Has a bluish color. Cool. That's why it's called ceruleus. Now, this is a nucleus. So the axons of the locus ceruleus, I'm going to just call this LC, project, which means that they extend to higher brain. So remember where we are. All right. So now we're down in here. So this region's in this locus ceruleus. That's where the cell bodies are, right? Axons come up and you extend up to the brain. All right. So that's what I mean when I say higher brain regions.
I have a question.
Okay, just a moment. I gotcha. On your right regions. Yes.
So the reticular formation is also another subsection of the pons.
That's correct.
Okay, so there's the reticular formation, and then there's two additional.
That's correct. I mean, yes, that's a great question. Yes. So now what do these do? Why am I pointing this out? Because the neurons of the locus ceruleus release the neurotransmitter norepinephrine. I'm going to abbreviate as NE. These neurons release the neurotransmitter norepinephrine, and when your sympathetic division of your autonomic nervous system is activated, guess what neurotransmitter those neurons ultimately release? Norepinephrine. Okay, so one of the effects of amphetamines. Amphetamines don't just affect dopamine. Amphetamines also activate the neurons in the locus ceruleus. Boom. We get the release of norepinephrine, which contributes to the alertness that we'd be seeing in people with amphetamines, or taking amphetamines, and the reduction in sleep. Okay. So what we'll be doing is we hit some of these major brain areas, especially brain areas that are going to be releasing neurotransmitters in parts of the brain. I'm going to always try to bring some drug effects in there right away so we can start seeing. What do you think? Another? We'll get to that later. Okay. That's one. The next one. Allison, don't freak. I'm just going to slide up the screen for a minute to use the board.
Okay.
Wow. Never mind, Allison. She can't see that. All right. Woo! I'm going crazy. All right. Drug-free day, folks. Drug-free day. Okay, can we even see that? No, we cannot, because that board stinks. Okay, second area we want to work on are the dorsal and median brachynuclei. By the way, has anyone heard of the locus coeruleus? You have. Okay, dorsal and probably dorsal and median middle, raphe nuclei. Dorsal and median raphe nuclei. These axons release the neurotransmitter serotonin. Bing, 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 otherwise abbreviated as 5-HT. So, these are also in the brainstem. Very important for, now we see alertness, now we see serotonin, right? Depression, okay? Depression is oftentimes thought to be impacted by levels of serotonin. Depression is also thought to be affected by levels of norepinephrine. Why? Well, I'm not alert. I'm not going to pay attention to anything. Nothing seems to like grab me. Okay? In the brainstem. Very cool. Devin, this is for you. LSD. Yo. Ding, ding, ding. Something, something, Devin. I'm going to come up with something at the end. All right. LSD produces its hallucinations by inhibiting the function of the raphe nuclei. So serotonin levels then in the brain just go boom, bottom out. Hallucinate. Yes?
So it's like the pond is like the big like umbrella, and then it's like the locus coeruleus and the brachynuclei beneath that.
They're in there.
Okay.
They're in there. That's a great question, Julie. So they're in here. Those centers are in here. Those cell bodies. Those nuclei are situated in this pond, and then the axons project up. And sometimes the axons also project down, but we're not going on. Okay? Great question. Other questions? Just related. You guys cool with what's happening here? Okay? We're going to talk about these areas a lot more in depth once we get to them. We're going to go over general brain structure, general neuron function, synapse function, and then we'll start zeroing in on some of these, and then we'll start talking about drugs. Okay? Cool. Awesome. Are you with us, Allison?
Yes.
Good. All right. And you know what I'm going to do is I will ultimately, I'll post the completed slides that are here, so that way if you guys are worried about the spelling or things like that, especially for you, Allison, I'll post those so you can get the right spelling, okay?
Yeah, I was just kind of winging it on some of those spellings.
Doing it. Oh, we're halfway there. Oh, hey, mesencephalon. Wait, we haven't talked about the cerebellum yet. Wow, cerebellum. Cerebellum. Where is it? It's back here. These beautiful cerebrum. Cerebellum. It's an Italian word. Okay. Kind of looks like the cerebrum a little bit. There, cerebellum. It processes basically sensory motor information. And it helps to coordinate smooth motor movements. So it's going to process sensory motor information like visual, audio, body position. Like visual, audio, and body position. So if I'm moving my hand towards something, the owl, ooh, I have an idea that I'm getting closer to that. And one of the brain areas that's actually is actually integrating some of that information is my cerebellum. Alcohol inhibits the function of the cerebellum. So that's why one of the tests is like this thing, and it can't touch my nose. Why? Because I don't know where my nose is. Why don't you? Because your cerebellum is inhibited. I can't feel my face. Okay, so alcohol does that. You get some slurred speech, staggering.
So it helps coordinate smooth motor information?
Yes. Yes. And oftentimes too, the cerebellum, some complex movements. So if you learn a complex movement, sometimes that information is stored in the cerebellum also. Okay, now we can start talking about the meat. Yes, Julie.
When you say complex movement, what do you mean by that? Like skipping?
Skipping, well, anything that's beyond just the normal.
So is it like riding a bike, like you want to fly into your seat, you just like get on there and ride it? That memory?
Yeah, well, that one, that's a great example because there you got body position and all kinds of things. Diving, maybe some gymnastic kind of things. So, yeah. But a lot of it is based on keeping you oriented in your environment. That's one of its main functions, is to help keep you oriented in your environment properly. And you saw the pictures of the neurons in the cerebellum. Do you remember the Purkinje fibers? Mm-hmm. We're going to see a picture of those. They're crazy looking. But anyways, okay. Mesencephalon. Yay, finally. I've only tried 300 times to get to this slide because I thought my slides were whatever. DFD, drug-free day. Just remember that. It's always a drug-free day with Father Sean. This is being recorded, right? Whatever. It's all good. We're all here together. Okay. Mesencephalon, midbrain. Like the midbrain. Midbrain's got two regions, tectum and the tegmentum. Tectum and the tegmentum. The tectum has two major regions. The superior colliculus, colliculi, colliculo, collicula, colliculus, and the inferior colliculus. So when we're using terms like superior and inferior, we don't mean that one's the boss of the other one, right? So in anatomical terms, when I say superior, it's above. Inferior is below. So let's look where we are again. All right, we're in the purple area now. So superior colliculus would be up in here. Inferior colliculus down here, okay? If it's in the text. All right. Okay, cool. The superior colliculus is part of the visual system. All right. And the inferior colliculus, it's part of the auditory system. So these two regions they help with processing of visual and auditory information. All right, basically. Okay. All right. The tegmentum. That's the tectum. Now let's talk about the tegmentum. I want to focus on one major area in the tegmentum. It is called the periaqueductal gray. Otherwise known as the PAG. PAG, the periaqueductal gray. Moderates pain, sensation of pain. Moderates sensation of pain. 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 So the tegmentum contains the periaqueductal gray. This area is much more relevant for our thinking here, for our class. If you electrically stimulate the periaqueductal gray, pinching you and prodding you and doing all sorts of things, you won't feel it. You don't feel the pain. So if you electrically stimulate or if you activate the periaqueductal gray, you experience analgesia. You can still detect heat, so you can feel, you would be able to feel that people are sticking things or pulling your teeth out. Oh, okay, you know what I'm saying. So you can still feel that. You can feel heat. You can feel pressure. You can feel touch. But you can't feel the pain. Kind of like when I just had my root canal a couple weeks ago. And that tooth numbed out. They're drilling. Dentist said, "You're going to feel a little pressure, but tell me if you feel pain." Okay. And we're gonna hollow out the inside of your root here. Man, has anybody ever had one of those? And you swear that they're sticking like a 5-foot drill into your head, because they're drilling. You can just hear like bone like crunching away, and you feel the thing moving in your head, and you're thinking, oh, that can't be good. And then there was this where the drill all of a sudden like went like boom, way up in, and I jerked. And he said, are you okay? Did you feel pain? I said, no, I just felt like a lot of pressure in a place I've never felt it before. He said, well, that's good. Well, you know, whenever you did that, a whole bunch of pus just flew out of your tooth. Great. So, anyways, stimulate the periaqueductal gray. Hey, get ready, Allison. It's going to be a crazy semester. But anyway, so let's link together our morphine story. So I turn on, I activate, doink, I put the light switch on the periaqueductal gray. What was the drug effect? What was the drug action? What was the drug action of morphine?
Activate the opioid receptor.
Activate new opioid receptors. What's the drug effect that we want? Analgesia. If I electrically stimulate the periaqueductal gray, what's an effect? Analgesia. What's a brain area that probably has lots of new opioid receptors? The periaqueductal gray. In fact, it does. All right. That's one of the ways that morphine exerts its effects. Okay. Cool. See how this drugs and behavior and things, see how it all relates, okay? Now, we've got two other important areas in this mesencephalon, two other nuclei that we need to bring up. Two other nuclei, okay? And I'm going to, these are all part of the tegmentum, by the way. I'm sorry, these are all part of the tegmentum. So the first one was the periaqueductal gray, the PAG. The second one is what's called the I thought I put Niagara. The substantia nigra. The substantia nigra. Named so because the neurons here, so just like in the locus coeruleus, it's named because those neurons look bluish in color. In the substantia nigra, this region, if you look at the brain and the brain slice, there's a very dark region where those cell bodies are. That's why it's called the black substance. That's what it means, because those neurons actually look black in appearance. And this region is important it's another region that's important for helping coordinate fine motor movements, let's say smooth motor movements. Smooth motor movements. Important for smooth, we're going to call it smooth motor movements. And almost done. Parkinson's disease. We'll get to this and then we'll get back to both of you. In Parkinson's disease, and I'm going to always abbreviate disease with the DX. In Parkinson's disease, you observe significant cell death in the substantia nigra. In Parkinson's disease, people diagnosed with Parkinson's disease, there is a significant amount of cell death in the substantia nigra. And yes, so question.
I'll just wait till later. It wasn't covered.
Yeah, I'll just wait.
Okay.
Is this like area like connected to the cerebellum? Like such a smooth motor movement?
Wow, that's a good question, and I need to look that up. Ultimately, yeah, complicated. But I'll get back to you on that, okay? Finally, last area in here. It's called the ventral tegmental area. We are going to cover this area in depth, in depth, in depth. It's abbreviated VTA. Anyone ever heard of this area, VTA? Yes.
So is the ventral tegmentum still in the tegmentum, or is this
This
a
is
separate area?
all three of these.
Okay.
Periaqueductal gray,
Okay.
substantia nigra, VTA. They're all in the tegmentum. The neurotransmitter here. Bum, 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 dopamine. That's the I feel good neurotransmitter. By the way, substantia nigra also uses dopamine. And we'll pick up here, but let's see here. Well, we got a lot to go yet. So, basically, there's two pathways coming out of the VTA. And we're going to go over this on Tuesday. So, the one pathway goes to the limbic system. And since it originates, since this is part of the mesencephalon, that's called the mesolimbic dopamine pathway. And all drugs of abuse activate the mesolimbic pathway. All drugs of abuse lead to a significant increase in the release of dopamine from these neurons. There's another pathway, we'll go over this again on Tuesday, so I'm just introducing it now. There's another pathway that goes to the cortex called the mesocortical pathway. And those neurons, so if you activate that pathway that releases dopamine in the prefrontal cortex and some other areas, that's important for regulating cognitive function. Dopamine is not just about pleasure, it's also about thinking. All right. Was it good to get into some material today? Good. I would continue with your reading, and I would start working down through the synapse. So on the second part of the reading schedule. All right, so Allison, I'll be sure to post the completed slides online for you.
Okay, thank you.
All right, do you have questions?
No, I think I'm good.
Okay, Julie, what was your question?
Oh, my comment was just that I liked your Crocs.
Oh, so when you look at Crocs, you're getting dopamine release in your nucleus accumbens, makes me feel happy.
I have like 5 pairs of socks. I love them. Do you have other colors or just the black?
I have a pair of blue ones that are all enclosed for lab,
Ooh.
except they sent me the wrong size.
Oh, that's not good.
They're like 2 sizes too big, so they look like, they're big enough for, I don't know.
The Ronald shoes.
Yes. See you, Allison.
Thanks for the Sean.
I'm gonna go.
See you guys.
Okay.
Have a good day, Sean.
See you, Allison. Oh, there you are. All right.
Have a good weekend.
Thanks. So Emily, I was excited to see that you took the class.
Yes, I'm actually really excited for it. I was like, I like took it the first day. I was like, oh my gosh, I'm really gonna love this class. So, yeah.
I hope it's a good class.
Oh, I'm so excited for it.
Come in. What's up?
Nothing. I want to see if they fixed this yet.
No.
Apparently not.
Did you guys break it last night?
No, it wasn't working on the teaching instruction there. That's why those are there.
Mm.
Then I went to my classroom last night.
Yeah.
Said you'll not work. Like, how did you?
Oh,
Yes, I do.
but I guess this is their work that they're working on.
Yeah.
Instead of actually coming in and fixing it. That's where we are, Phil.